Okay, in Unit 2, we're going to do the following objectives, starting with Objective 1, finding intervals where the function is increasing or decreasing. So I have a basic application here. Hiker is changing altitude when hiking is shown below. Identify the intervals where the altitude is increasing, decreasing, and constant. Okay, so we don't have anything labeled on the y-axis, but that's not important. What we need to know is when I ask questions about increasing, decreasing, for which x values is y increasing or decreasing. That's how to say it in a more math way. For which x values is y increasing, decreasing, and constant. So you can see here, let's finish this labeling. These are going up by 2 hours. And I did this on purpose to not put y values here because we're only interested in the x. So I could answer this question. From 0 hours to 6 hours, my function's increasing. X values. From 10 to 12, my function's increasing. So two different intervals where it's increasing. That's increasing. Decreasing, it's easy to identify on the graph, but can you write it the proper answer? Decreasing from here to here, right? If we knew the y values, the common mistake would be to say from y, say that's 8,000 feet and that's 6,000. Decreasing from 8 to 6. 8,000 to 6,000. Not correct. You're always doing the values of x for which y decreases. So in this case, 6 to 10. Constant looks like we start here and we end. We don't have an arrow here, so if it's stopping there, it looks like 14. Call it 14.5. Constant. The x values go from 12 to 14.5. Okay, so same idea here. Let's do, now that we have these going to infinity, it'll change our process a little bit. Let's go increasing, decreasing, constant. Go ahead and pause, see if you can get this. So it's going to increase from x value negative infinity as I go from left to right to negative 1. Then it's going to decrease from negative 1 to 0. X values. It's going to increase from not from negative 4 to 0, but from 0, x value 0, till I get to 2. 0 to 2. Well, let's do a constant one. I think I'm going to change my mind on that one. I think it's constant from 1.5 to 2.5. So let me adjust that. 1.5 to 2.5. So increasing, I think it goes from 0 to 1.5. I got to change that one. All right, we're moving along here from 2.5 till 3.5. It's going to increase. X values, right? Notice I'm not writing that's a y value of 4 or 4.5. I'm not writing that on there, just the x values. And then it's going to decrease the rest of the way, 3.5. Forever to infinity. Okay, relative max and min concept is relatively easy. You can define it as function changes from increasing to decreasing. We got a maximum. A local max, what does that mean? Well, it's not this value for 16 isn't the highest number on the whole graph because it's going to go forever, but it's the maximum relative to numbers around it. And the same idea here, right? And it's easy to identify in the graph, just a peak at a high point or a low point on the graph relative to values around it. Let's talk about symmetry. To be symmetric on the y-axis or symmetric around a vertical line, if you wanted to put an axis in here, which we're going to do in a second, it's symmetric on the y-axis if you can hold a mirror right on the y-axis and it reflects, it makes a reflection, half of the graph reflects and makes the whole graph. Or if you fold a piece of paper on the y-axis, this side would lay on the top of that side. That's symmetry around the y-axis. Same idea for symmetry around the x-axis. If I creased my paper here and folded, this end would end up on this end. This guy's symmetric around y. This one's a little trickier, to be symmetric around the origin. This one you have to kind of use your imagination for. Let's see if I can do this. The idea here is if you rotate, graphically, if I rotate this 180 degrees, the whole graph, like I kind of put a pin there and rotate it, then the graph, you get the same picture. This piece will end up over here, and this piece would end up over here. Okay, let's see if I can do that. Because this lets me rotate. So rotate 180 degrees. 180 degrees. And you're right back where you started, right? It's the same picture. Okay, so that's a little bit harder to see. But that's what it means to be symmetric around the origin. Mathematically, if AB is on the graph, then negative A, negative B is on the graph as well. Okay, this is how we do it algebraically to test for symmetry. You can read these. And I'm going to show you what these mean in practice. So I want to know if this thing is even or odd. So what you always do is you replace x. I'll use function notation. And I always plug in a negative x. I'm going to do that for both of these. Always start the same way. If we get the same function, then it's even. Okay, if this ends up being the same function as the original function, then it's going to be even. That is, if the negative value produces the same output as the positive. Graphically, right, if I plug in A, positive A, I get B. But if I plug in negative A, I also get B. Right? This is an even function. Even is the same as symmetric around the y-axis. Okay, and that's what we're doing down here algebraically. And you see what happens here. If I square a negative value, I get the same thing as if I were to square the positive. So I can abbreviate, or I can replace negative x squared with x squared. And anything with an even, you see where it gets its name, with an even power, same thing happens. Right? Negative x to the fourth is the same as x to the fourth. And look what happens. When I plug in a negative x with those couple operations, I get the same function as I started with. So I know this is even, which also means it's symmetric about the y-axis. Okay, let's see what happens with this. This guy is going to be odd, I think, but let's see how we show that algebraically. So you go 2 negative x cubed minus negative x to the fifth. Okay, what's negative x cubed? How can I rewrite that? Well, remember, here's one way to think about it. Raising something to the third power means negative x times negative x times negative x. Negative x times negative x is positive x squared, and then times another negative x would give you negative x cubed. So in other words, a negative number raised to the third power is the same thing as the number raised to the third power, make it negative. And that's the concept I'll use here to take a look at. Same thing here. So negative, sorry, that should be negative x to the fifth is how I should really write that. Because that indicates I'm taking a negative number raising it to the fifth power. But we know that's the same as raising x to the fifth power, making it negative. And these two negatives will end up being 1 plus. Okay, so that's the work involved to show what happens when I plug in a negative x in this function. And look what I get. I get the opposite. That is, negative 2x cubed is my output. It used to be positive 2x cubed. And the x to the fifth was negative, now it's positive. If I want, I can factor out a negative 1. Sometimes that's helpful in these. And I'll change the sign of everything. Right, so this tells me this is my original function, and this is the opposite of that, or the negative of that. And that means it's an odd function. Right, if I input an x, output a y, then what else has to be on the graph? Input a negative x, output a negative y. Right, this is the opposite of the original function. So that corresponds with symmetry around the origin. One of these guys, input a positive, get an output positive. But if I input a negative, I get the output of the same value but negative. And that means it's odd, and it also means it's symmetric about the origin.